In the name of Almighty God, I'm Master Sankosha, and today I want to talk about thermodynamic system in physics GRE. Now I want to go through the subsection 4.2.2 gases and equations of states. Thermodynamic systems are specified by an equation of a state that constrains the value that the state variables may assume. The most famous example of this is the equation of state for an ideal gas. PV is equal to N chi BT, where P is the temperature, pressure, V is the volume, N is the number of particles, and T is the temperature. You probably know this as the ideal gas law, describing how the state variables P, V, and T are related. The only other equation of state you may see on the exam is the equation of state for the van der Waals gas. The van der Waals gas has particles with non-zero size and a pairwise attractive potential, and the equation of state is pressure plus n to the power of 2 multiplied by r divided by v to the power of 2 multiplied by v minus mb is equal to n cos bt, where r measures the attraction between particles and b measures the size of the particle. Clearly, I is equal to b is equal to 0 reduces to the ideal gas law. You should definitely not memorize this equation as it will be given to you if needed, but you should be familiar with its interpretation. Now I want to go through the type of processes. The subsection 4.2.3 thermodynamic processes can be classified into several types that have important properties, mostly relating to holding certain variables constant. The words used to describe many of these processes are often used interchangeably, but this is sloppy. There are very precise meanings, and it is crucial to keep definitions strict to know which formulas apply. Here is a list of the most important processes you will encounter on the GRE. The first type is reversible process, a process that proceeds an infinitesimal steps, such as that the system is in equilibrium at each step, and each infinitesimal step can be reversed by somehow changing the state of the system. A common example is slowly heating a gas in a container of flexible size. As an infinitesimal amount of heat is added, the gas expands and comes to equilibrium after enough time has elapsed. This can be reversed simply by cooling the system by removing an equal amount of heat. Reversible processes imply several important conditions. If the process involves a gas, the work done in each infinitesimal step is given by derivative of W is equal to P derivative of V is reversible. Note that this is not true if the process is reversible. See free expansion below. In addition, the total entropy change of the system and its surroundings must be zero. The entropy of the system by itself can change, however, and is given by derivative of Q is equal to T derivative of S, reversible based on equation 4.18, where T is the temperature and derivative Q is the heat input. The integral form of this equation is delta S, or delta entropy is equal to integral derivative of Q divided by temperature, which is just the lower bound of the second law expression based on the equation 4.15. Every reversible process has the minimum possible entropy increase for a given derivative q. Notice that if a derivative q is or delta q is less than 0, delta s or delta entropy is negative. There is no contradiction here. Cooling a system reduces its entropy. So, for increasing the entropy, we need to give the temperature, but increases the entropy of its surroundings by an equal amount because of the heat deposited. So the total entropy change is zero. Finally, notice that if the initial and final states of the system are the same, the limits of integration degenerate onto each other, and delta S is equal to zero. The entropy change of a system undergoing a reversible cycle is zero. Now, the next process is quasi-static process, a process that happens infinitely slowly, so that at each instant the system is thermodynamic equilibrium. Reversible processes are always quasi-static, but a quasi-static process need not be reversible in general. So the next process, adiabatic process, the process for which the delta Q is equal to zero. No heat is exchanged between the system and its surrounding. The next process is isentropic process, which is reversible adiabatic process, a process that is both adiabatic and reversible. One can prove that a process is reversible and adiabatic if and only if it has zero entropy change and is an isentropic process. Here we mean that the entropy change of the system itself is zero, and consequently the entropy change of the surrounding is zero as well. Compressing a gas in a cylinder by pressing down a piston is prototypical example. By applying a very small force, the piston is displayed small amount. Each compression step can be reversed by removing the force, which causes the gas to expand again and the system to return to its initial state. Since no heat is exchanged during this process, adiabatic compression is isentropic. One major reason that this type of process arises in problems is that for an ideal gas undergoing an isentropic process is PV to the power of gamma is equal to constant, where gamma is equal to CP divided by CV is the ratio of the heat capacity at constant pressure P to heat capacity at constant volume V. There is a particularly nice formula for gamma for ideal gases, which we discuss further in section 4.2.5. Warning: past GRE have been known to use adiabatic to mean reversible adiabatic. Keep the more resistive definitions in mind, but prepared to be flexible and suddenly based on the context, because the GRE often doesn't define its term in the test questions. Is something processes a process for which some state variable is held constant? Isothermal means the constant temperature. Isobaric means constant pressure. And isochroic means constant volume. Time memorizing these terms is completely unnecessary. The key to figuring out the work done by a gas in such a process is to use the definition of work 4.17 supplanted by the ideal gas law equation of state 4.16 to solve for P in terms of the constant variables. For example, if P is constant, it can be pulled outside the integral and W is equal to P multiplied by delta V. If the temperature is constant, then solve for pressure in terms of the temperature. Pressure is equal to N Kelvin temperature divided by V, which is given. W is equal to MB Kelvin temperature integral derivative of V divided by V. If V is constant, then no work is done since derivative of V is equal to zero. The isothermal process is perhaps the most common, so get familiar with the form of the integral and appearance of ln v from the integrating derivative v based on the v. Free expansion. This process occurs when a gas suddenly expands from a smaller region to a larger region. Think of a balloon pumping, where the gas initially inside the balloons rush out to occupy the whole volume of the room. The temperature of initial gas doesn't change during free expansion. So we have PV is equal to piperine, vaporine free expansion. Note that free expansion is adiabatic but not reversible. One cannot force all the gas molecules back into the smaller volume once they have expanded, simply by changing the state variables of the system by the inertia. Free expansion is the prototypical reversible process, just as irreversible as an egg breaking. The fact that this process is irreversible means that there is an entropy change, despite the fact that delta Q is equal to zero. Equation 4.19 simply doesn't apply to irreversible processes. We will see in example 4.2 how to calculate the entropy change. Similarly, note that despite the fact that the volume change, the gas doesn't work. This is consistent with the first law. Delta U is equal to zero at a constant temperature. Q is equal to zero since the process is adiabatic, and W is equal to zero. So we trivially get zero is equal to zero minus zero. And also notice that don't drink the inertia because it's possible that it evaporates you. You see, when you eat it, you show especially chlorohexidine, hexidine. It's some sort of substances that really can evaporate, and the gas, such as balloon, evaporate from you. It's some sort of very dangerous that has some sort of digestion in your system, that your system suddenly evaporate, and you must look for yourself under the bed. Another section is 4.2.4, relations between thermodynamic variables. It's a very amazing section, thermodynamic system. Just be careful that not evaporation happens in your system. Equations of state tell us what states are accessible to a particular system in terms of the system's state variables. What if we are interested in other variables that are not the state variables of a system? Surprisingly, how would we calculate the entropy of an ideal gas, for example? There are a larger number of thermodynamic identities that relate, under varying circumstances, all of the variables that we have been discussing. The first identity is useful, that is often called the fundamental thermodynamic identity. It relates the differentials of state variables U(s) and V. du is equal to TdS minus PdV. This equation is simply the infinite small version of the first law. 4.14 du is equal to delta Q minus delta W, supplanted by the definitions 4.18 and 4.17 for delta Q and delta W respectively. Notice that we write delta Q and delta W, not dq and dv, because d means the derivative, but delta is a changing. This is because Q and W are not state variables but refer to small quantities of heat and work added or to or down by the system respectively. In contrast, U is a state function, a mathematical representation of the internal energy of the system, which can thus be sensibly differentiated. Finally, note that based on the 4.21 applies to all infinitesimal changes of state, not just reversible ones. This needs a tricky bit of reasoning, so this fact is best simply memorized. The fundamental thermodynamic identity also implies a definition of temperature and pressure. T is equal to the delta U divided by delta S, and we can have this with a lower boundary is V, based on the V, and P is equal to minus delta U divided by delta V, and based on the entropy. The vertical bars refers to holding subscript variable constant. So equation 4.22 holds at constant V and constant volume, and equation 4.23 holds constant entropy. Another important class of thermodynamic relations are the Maxwell relations, which relate partial derivatives of the thermodynamic variables. From the expressions for temperature and pressure above, we can create mixed partial derivatives and determine delta p divided by delta s, and we can constant, because now at this moment we know that what's the meaning of the vertical bars. Here vertical bars means that the volume is constant is equal to minus delta t divided by delta v, and here in the right hand of the equality equation is that we have entropy as constant variable. There are three other thermodynamic potentials, which we give here for completeness. Tau, you almost certainly will not need them for the GRE. Delta enthalpy is equal to temperature ds plus vdp dr is equal to minus entropy dat minus p dav dag is equal to minus s dat plus v dap. The associated max variation are such as this formula. The next is heat capacity. The heat capacity of an object is the amount of heat it takes to change the temperature of that object. More precisely, we can define the heat capacity at constant volume and pressure as such as the delta Q divided by delta T, and we make a constant at volume is equal to CV, and delta Q divided by delta T, we keep pressure as a constant is equal to CP respectively. And this respectively given our admonition to be careful about writing delta Q rather than delta Q. The abuse of notation delta Q may seem strange, but it is a common one. Just make sure delta Q only shows up when taking a derivative with respect to something, and not as a total differential as in equation 4.21. The more common one is CV, because referring back to the fundamental equation 4.21 constant value is equivalent to dv is equal to 0. So we can differentiate both sides with respect to t and get derivative q divided by derivative t based on the volume is constant is equal to derivative u divided by derivative temperature. Hence, differentiating the energy you obtain from the equipartition theorem gives you COV. In fact, for an ideal gas, there is a very simple but very tricky to derive relation between CP and CV. CP minus CV is equal to N chi B when air is the number of particles. Note that this is true for any ideal gas, monoatomic, diatomic, or something more complicated. This in turn immediately gives you the ratio gamma you need for an adiabatic process. If you know the internal structure of the gas, for example, a monoatomic gas has internal energy 3 divided by 2 kBT per particle from the equipartition theorem. So we have CAV is equal to 3 divided by 2 NKB, which is given CAP is equal to 5 divided by 2 NKB, which is given gamma is equal to CAP divided by CAP is equal to 5 divided by 3, as defined. CP and CV are extensive variables because they depend on a quantity of a substance being heated. If we normalize to the mass of the material, we get an intensive quantity C called the specific heat or specific heat capacity, typically in unit of J called to the power of minus 1, G to the power of minus 1. From dimensional analysis, we can remember the formula for the amount of energy Q required to heat a mass M of a specific heat C by delta T degrees, as Q is equal to mc delta T. The specific heat capacity of water is famously equal to 4.18 joule per kilogram G at standard temperature and pressure. Because of this, specific heats are sometimes quoted in units of calories rather than joules. One calorie is set to be 4.18 joules, so that the specific heat capacity of water is conveniently 1 calorie per Kelvin G. We should note that the terms heat capacity and specific heat are often used interchangeably, and if the distinction is necessary, the unit and constant should tell you which one is meant. Another subsection 4.2.6 model systems to thermodynamic systems are almost guaranteed to appear on GRE, heat engines, and ideal gases. Gases also provide a nice system for studying the propagation of sound waves. Heat engine P minus V and T minus diagrams. A heat engine is a process that converts heat into work. Schematically, the heat engine absorbs some heat QH from a hot reservoir at TH, expels QC of this to a cold reservoir at TC, and converts the remainder in work. W is equal to QH minus QC. Since energy QC is not converted into work, the efficiency of the heat engine is equal to 1 minus absolute QC divided by QH. Note that there are various sign conventions for QC and QH, but the absolute value signs make sure is less than 1 always. The maximum theoretical efficiency for a heat engine is equal to 1 minus Tc divided by Th, which is in fact the efficiency of idealized Carnot cycle. The Carnot cycle consists of 4 steps. First, the gas undergoes reversible thermal expansion at a high temperature Th. Entropy increases from S1 to the S2 during this process. Next step is the gas expands adiabatically at constant entropy until it has temperature Tsc. The gas then is compressed at constant temperature Tsc and entropy decreases from S2 back to S1. Finally, the gas is compressed adiabatically. So you see it's a thermodynamic cycle. We call it as a Carnot. Figure point 4.2 shows an example of Carnot cycle in the T minus S plane, increasing the temperature from Tc to Th. The entire process is thus a rectangle in the Ts plane, illustrated in figure 4.2. Since the system returns to its initial state, this change is in internal energy over the cycle is zero. Delta U is equal to zero. The first law then tells us that Q is equal to W. The heat input in reversible processes is Q is equal to integral T ds. So we can compute the work by this formulation. W is equal to Q is equal to the integral T ds is equal to T enthalpy minus Tc multiplied by entropy S2 minus SF1. In other words, the work is the area in the Ts plane. Bounded by the Carnot cycle, problems on GRE often involve analyzing cycles of the systems in pressure volume or entropy temperature diagram. The Carnot cycle is just one example of a problem that can be analyzed with one of these diagrams. The similar example PV diagram is shown in figure 4.3. This diagram could represent an ideal gas that undergoes compression at constant pressure and increase in pressure at constant volume via heating, and then is thermal expansion. To find the work done during the process, just find the area in the PV plane. Since that's the integral P, the V instructs you to do. It is important to note that the areas are signed the quantities. If you reverse the direction of the closed path bounding the area in question, you flip the sign of the area and hence the sign of the work. This is often a crucial distinction since it tells you whether the system is doing work on its surrounding or vice versa. You can determine this sign with a right hand type rule, but it is just as easy to use physical reasoning. The gas does positive work as it expands, And for a given volume change, delta V does more work at higher pressure. So imagining a rectangle in PV plane, the gas does positive net work when the upper horizon edge is traversed left to the right, and the bottom edge is traversed right to the left. Similar analysis holds for TS diagram. So to summarize, clockwise paths in PV and TS plane do positive work. So both are figure 4.2 and figure 4.3. Because there are clockwise paths, they are doing positive work. The left side figure 4.2 is a rectangle. The right side we have a triangle. An example of circle in the PV plane that walk down is the sign area enclosed by the curve. Just remember which axis goes where. Now I'm going to go to another section. Monatomic ideal gases. Since the ideal gases are so common, at a minimum you should know the internal energy, the entropy, and the root mean square velocity. Sometimes it's handy to know the partition function because it allows you to calculate so many observable, but it is not essential knowledge. The Hamiltonian for a particle and ideal gas is just the Hamiltonian for a free particle in 3 dimensions. So using equation 4.11, with h is equal to p to the power of 2 divided by 2, and we have the partition function for single particle. Z1 is equal to 1 divided by h to the power of 3 integral e to the power of minus beta p to the power of 2 divided by 2m multiplied by d to the power of 3 p d to the power of 3x is equal to v divided by h to the power of 3 multiplied by 2p m chi b t to the power of t divided by 2. For a gas of n identical particles, the partition function is just the product of a single particle partition functions. Is just the product of all single particle partition functions times them normalize a factor 1 divided by n factorial for identical particles, and you see Zn is equal to v to the power of n divided by n factorial h to the power of 3 to the power n multiplied by 2p m chi bt to the power of 3n divided by 2. From this, we can immediately derive the internal energy of a classical ideal gas using U is equal to 3 divided by 2 n chi bt, which implies CAV is equal to 3 divided by 2 and chi b. From the discussion in section, you can turn this around and use the equipartition theorem to remind yourself about the factor of the 3 divided by 2 in the exponent of the partition function. Always these equipartition can divide the dimension to a less dimension. There are 3 quadratic degrees of freedom in the Hamiltonian, one for each spatial dimension, giving the factor of 3 divided by 2 in the internal energy. Related to the average internal energy of a gas is the RMS or root mean square velocity of a gas molecule. This is given by the V root mean square is equal to root mean square 3 bt divided by m. The rotational and vibrational motion of a gas molecule doesn't contribute to its velocity. A molecule can rotate however it wants, but if has no translational energy, its RMS velocity will be zero. The result of this is that the even tau monatomic and diatomic gases have different internal energies. The expressions for their RMS velocities are equivalent. This makes the formula very easy to remember. The factor of 3 comes from the 3 dimensions, and the rest of the factors come from dimensional analysis. We can also calculate the entropy of an ideal gas just by differentiating the partition function. using equation 4.8 and derive equation 4.9, which we sadly repeated here for convenience, as equal to nk b multiplied by ln v divided by m plus 3 divided by 2 ln t plus 5 divided by 2 plus 3 divided by 2 ln 2 pm chi b divided by h to the power of 2 multiplied by p.at. This expression is useful for demonstrating the entropy of mixing as shown in example 4.3. Sound waves in gas. Sound waves need a medium to which to propagate, and in most everyday situations, this medium is a gas. As discussed in chapter 3, the speed of sound in material is given by CD is equal to square root meter K divided by density, where K is the mean of stiffness called the bulk modulus and rho is the density. The stiffness of an ideal gas is tricky to define, but the general result is K, or stiffness, is equal to gamma P, where gamma is equal to CFP divided by CFV and P is the pressure as usual. From this, we have general results that the speed of sound in an ideal gas is just C is equal to square root of gamma pressure divided by density, or rho. This formula is also simple to memorize. High pressure means faster speed of sound. Higher density means lower speed of sound. And the square root comes from dimensional analysis. Notice how that this formula contains an implicit dependence on the temperature, since rho is equal to Nm divided by V. The ideal gas law gives P divided by or pressure divided by rho, or density, is equal to P divided by Nm divided by V is equal to PV is divided by Nm is equal to NKBT divided by Nmm, so that the speed of sound can be written C is equal to square root of the gamma chi bt divided by m. Thank you so much for watching my tutorial video today. Today is the second day of June 2026. Time is 12:15 p.m.